Everybody's coming in. Brilliant. Okay, well, thank you all for coming. Yeah, I don't know if any of you were here last week, but this is a free session. It's a free session on various subjects to do with chemistry, with science in general, and what these are all about. It's really designed to, I guess, try and explore some of the subjects a little bit more than perhaps you would do in your school. Some of the things that perhaps you don't get to cover in the normal curriculum. Some of the more the areas perhaps that are a bit more applied, a bit arguably even a little bit more interesting. And what I've tried to do is accommodate all the different grades that of students that there are coming in. So the idea is to try and make all of this as accessible as possible to as many students as possible, whatever grade it is that you are doing. So hopefully you'll enjoy these sessions. Hopefully you'll spend more time with the student shed as well, and hopefully you'll learn something tonight, and you'll get something out of the subject. Now, anytime, please do feel free to ask questions about this. And we'll talk all the way through it, and we'll explain things as we go through. Okay, then what I'm going to do now is bring up the presentation, share it onto the screen, and then we'll get to it. So tonight's workshop is going to be about hydrogen bonding, water, and ammonia. So let's get to it. And there we are. Okay, all right. There is the front screen. So what we're going to be looking at tonight is an overview of these areas here: van der Waals forces, water, hydrogen and the structure of water, hydrogen bonding with reference to water, the dipole and the dipole moment, hydrogen bonding, structure of ammonia, what hydrogen bonding is with reference to ammonia, shapes of ammonia and water. And for me, the most important bit, or the bit that hopefully is the most interesting for you, the most relevant, the most applied bit, is the part about why all of this is so important. Because a lot happens, because sometimes, you're in school, sometimes you think, what am I learning this for? That's another thing about these sessions. What we want to try and do is try and get to explain to you why it is we're learning these things. Okay, so right, okay then, van der Waals forces then. In what are called simple covalent substances, and what they are is non-metallic elements in the periodic table. What these substances have is very, very strong bonds between the atoms which make up the molecules and the compounds. Have you all done or at least looked at atoms, molecules, the particle, even in the particle model? Have you all done things like that? Or at least heard of it?
I have.
Yeah, cool. Okay, all right. Now, that's a little abbreviation here. With these substances, the melting point and the boiling point tend to be low, because the individual molecules that make up the individual molecules that they are easily separated from each other. And this explains why what are called most simple molecular substances are gases and liquids at standard room temperature and pressure. And that means as things are at sea level. So that's what that room temperature and pressure. So what that means is temperature about 20 degrees, the room temperature is around you, and the pressure is 1 atmosphere. So as things are at ground level, at sea level, like when you're sitting on the beach, or when you're at home, when you're home, going through your life, really. Okay, next one is, these are just some examples of what are called some of the simple covalent substances that we're talking about. You would have seen, if you're doing GCSE chemistry, or you're in any kind of science laboratory, you would have heard of all of these substances before: hydrogen, water, hydrogen chloride, methane, carbon dioxide, and of course on the right here is ammonia on the left. All these dots and crosses mean on there, they represent the chemical bonds. So, and we're going to talk a little bit about how many bonds there are in the molecules. But we're not going to get too bogged down in that, because we do that, in another part of the chemistry curriculum that's called covalent bonding, where a lot of the bonding here is that we're going to mention here is explored in much more detail in those areas. So there are examples of some simple covalent compounds, covalent molecules. As liquids, they all have, this is the key bit, they all have attractive forces.
Sorry, I'm late.
So go on.
Hi, sorry I'm late.
It's all right, no worries. Don't worry. Don't worry.
Thanks.
Don't worry. You're here now and there's a recording, so it's fine. Don't worry about that. You're here now.
Thanks.
That's okay. No worries. No worries. You'll get the recording of this. That's fine. Yeah. Cool. Hi, Anna. Hi up. Okay. So where are we? Yes. All of these substances, they all have attractive forces between the molecules as liquids, but as gases, they don't. Because that's, if you think about the particle model, all the gases, they're all separate from each other because there's no bonds holding no attractive forces between the molecules. Okay. What happens though, as structures become bigger or there are more molecules, the combined strength of what we call these intermolecular forces increases. And what that means is just the forces between the molecules, not within them. So as you get more of these forces, or there are more as you get more molecules, sorry, you also get more forces. So the combined strength of the intermolecular forces increases because there are more molecules, and so there are more forces. Now, what this means is that when this happens, the melting point and the boiling point will steadily increase. And the point with these intermolecular forces is that they're not as strong as the bonding that there is between the atoms which make up the compounds. These forces are much, much weaker than the bonding which holds the actual compounds and molecules together. So that's the first point to get across, is that the forces we're going to be talking about today, the hydrogen bonding mainly, is these forces are a lot weaker than the chemical bonds which hold compounds and molecules together. Okay, so why are they called van der Waals forces? Well, the answer is very simple. They were discovered by this fella here. And underneath there's a little link to tell you a little bit more about him. He was I believe, it's a Dutch chemist. And what he established and worked out was that these forces are the attractive forces between simple covalent molecules. They're also called intermolecular forces. And as I said, they're weaker than covalent bonds and ionic bonds. And if you don't know what covalent bonds are or ionic bonds are, don't worry too much. And because if you haven't got to GCSE yet, you won't have covered them yet. But don't worry if you don't know what they mean. There's some more links later on where that will explain that. So the kind of example that what we're going to be looking at today, an example of an intermolecular force, is hydrogen bonding between water molecules or ammonia molecules. So really, we're going to be looking at both of those. Okay, and just so that you know, just to sort of show you very quickly, these are the types. These are the four types of chemical bonds. Two types of chemical bonds and the two types of structures that there are. So there's a quick slide there which shows you what the four main types of bonds are. And what a chemical bond is an electrostatic force between atoms which hold individual molecules or compounds together. And the type that they're called are ionic, simple covalent, metallic, and giant molecular. Okay, so covalent bonding, ionic bonding, and metallic bonding. And that's all there on the slide there for you to look at. All right, just so that you know that these here are the bonds between the particles, the atoms and the molecules that make up the substances. And what we're going to be looking at is the forces between the substances. And we're going to be looking at hydrogen bonding with water and ammonia. Okay, so what's hydrogen though? I suppose that would be a good place to start. It's the simplest chemical element. It has one proton in the nucleus. Does anybody out there know what a proton is?
A proton, it's the positively charged atom in the nucleus.
That's it. It's the positively charged particle in the nucleus. Well done, whoever said that. Fantastic. So it's in the center of the nucleus. It's got a positive charge, and hydrogen is the element that has only one proton in the nucleus. It was discovered by a scientist called Henry Cavendish in 1776. Hydrogen gas is made from two hydrogen atoms held together by a single covalent bond. It's an example of what's called a diatomic element, and there's links, and there's a link or two at the end which go into that as well. And it's found all over the Earth, and it's found everywhere in the universe too. It's found everywhere. Sorry, it's found everywhere, chemically bonded as part of what are called I'll start that again, as inorganic and organic compounds. And if those of you that were at the session last week or last month, sorry, on climate change, there's a very quick definition of what we mean by inorganic and organic compounds. Hydrogen has two isotopes. So in nature, there are three forms of hydrogen which exist, and we're just going to show you them here. So very quickly, you can see the atomic structure. Now, who's seen pictures like that before? Pictures of atoms, pictures of molecules, and looked at these before.
Pardon me?
Who's seen pictures like this before, like these sorts of pictures before, where you've got the center of the atom and the electrons that spin around it? And who's seen words like proton, neutron, and electron before?
I haven't seen that before.
Okay, all right. Like I said at the start, what we're trying to do, it doesn't matter too much for these sorts of lessons, for these sorts of sessions, but what we've got here is what's a representation of hydrogen in the nucleus in the center. This is the form of hydrogen that we're most familiar with. It has one part of the proton in the nucleus, and then sometimes it's called protium, and the other two are what are called the isotopes of hydrogen. So a hydrogen ion, that's one of these, when it loses this electron, all it is in the middle of the nucleus is a proton. A proton has a positive charge. So, which means it has a hydrogen ion then has a symbol called H+. All the H means is what hydrogen stands for. That's the chemical symbol for the element. And the plus means the charge that the ion has. So hydrogen ions have a positive charge, and this makes them really very, very quickly attracted to atoms or ions which have a negative charge. And as we'll see as we go through this, we'll see that this forms the basis of why hydrogen bonding happens and why it's so important. Okay, so we talked about water and ammonia at the beginning. Now, you're on an island, you're surrounded by water. I live in South Wales. It rains all the time here. We've just had some rain this week, which has been well needed. But water is everywhere. But what is it? It's made from two atoms of hydrogen and one atom of oxygen. Each hydrogen atom, that's that we showed you above, each one of these hydrogen atom has space for two electrons, for particles called electrons, which can spin around the orbit or the shell. Okay, but if you look at it, look at the picture above, each hydrogen atom only has one electron. So what it needs to do is get a second electron, and it does it with water by chemically bonding with one atom of oxygen. And what you have when that happens is a V-shaped molecule. And a molecule is a substance that's made up of one or more atom. And molecules can be compounds or elements. Okay, so carrying on with water. Here we are. Now then, another word here I don't want you to worry about too much, called a lone pair. Here is the formula for oxygen and a picture of water and a picture of water. It's made with two single covalent bonds, and what that means is that two pairs of electrons are shared. You have one electron from each hydrogen atom here, and it also has one electron from the oxygen atom here. So the two atoms share these two pairs of electrons. And what happens is you get a molecule of water. Now, what all a lone pair is these two pairs of electrons here. It just means that those electrons are not involved in chemical bonding. So they just spin around outside the nucleus. They're not involved in chemical bonding at all. That's why they're called lone pairs. It just means two pairs of electrons which are not involved in bonding. Now, this word here, electronegative, is just a fancy way of saying that oxygen has a stronger, has more of a negative charge than hydrogen does. So what you have in a water molecule is oxygen has a negative charge and hydrogen has a positive charge. Is everybody happy with that? Just this idea that the oxygen atom is negatively charged, and the hydrogen atom is positively charged. Yeah? Or everyone happy with that?
Yes, sir.
Yeah, cool.
Yes,
Cool.
sir.
Good. Right then. Okay, so with hydrogen, the hydrogen atom doesn't have any shells of electrons. Like we said, it's the simplest substance that there is. So when it loses the electron, all it has is the proton in the middle of the nucleus, which has the positive charge. Each oxygen atom has two lone pairs of electrons. And what this means is it can make hydrogen bonds with two different hydrogen atoms. And we're going to come to what hydrogen bonds are in a minute. But it's just this idea that these two electrons here can form hydrogen bonds with other atoms, with different hydrogen atoms. The oxygen atom, what happens is the oxygen atom attracts the electrons which make up this chemical bond here. So the oxygen pulls it towards itself. So it pulls what the oxygen atom does is it pulls the electrons towards itself. And what this does is it causes an unequal distribution of electric charge. In science and chemistry and physics, whenever you hear the word charge, all they mean is whether it's positive or negative. And what happens with an unequal distribution of charge is you get, with water, what happens is you get a negative charge on the oxygen atom, but a positive charge on both hydrogen atoms. And this creates in physics and chemistry what's called a dipole. That's just another fancy word that you don't need to worry about it. It means it just creates a difference in charge in between different ends of the molecule. Because the covalent bonds are really just pairs of electrons, they have the same charge. Now in science, whenever you have anything that's the same, negative, if it's the same thing, so positive or positive, negative or negative, or if you've done magnets, if it's the north and the south, if you get two of the same things coming towards each other, they come a point where they repel each other, they push each other apart. So if you've got covalent bonds which are electrons, that's pairs of electrons, the two electrons repel each other, but they're also pulled by the positive charge from the nucleus inside the oxygen and the nucleus inside the proton inside the hydrogen atom. But they can also be pulled by positively charged atoms which may be close by. So what we're trying to say here is that you've got this idea that negative and positive attract each other, and that causes these different forces, causes different arrangements of the atoms in the molecule. So the positive charge attracts the negative charge, or the negative charge attracts the positive charge. Depends how you want to look at it. So what you have then is water and ammonia. They have the same thing because they're what's called polar compounds. Now, if you look, what you've got here is another picture of oxygen, of water, sorry, and next to it you've got a picture of ammonia. The only difference, really, what do you know? What do you notice about the difference in these compounds? Anybody say what any differences between the two compounds that you can see, just in terms of how many particles there are?
Water has 2 hydrogen atoms, but ammonia has 3.
Absolutely, well done. That's absolutely right. That was looking for. Brilliant. So the water has 3 particles altogether, to 1 atom of oxygen, 2 atoms of hydrogen, and the nitrogen has, the ammonia has 3 atoms of hydrogen and 1 atom of nitrogen. So what you've got here, okay. Yes, Taja, you can. You will get a recording of this, and we can also send you the PDF and the PowerPoint as well. So the answer to that question is yes. Okay, so the polar compound. So what we have then is this idea then of what's called a polar compound, and what this means is a polar compound is one which is ionic. What that really just means bonding between metals and non-metals, or one that has a compound which has a permanent dipole moment, like ammonia and water. I'm going to come to what some of these words mean in a minute. What this is, though, this idea of polarity, or a polar compound, or a dipole moment, or how ionic it is, if you like, the substance is a measure of the extent to which the electrons, which are these particles here, are pulled towards one atom in the molecule relative to the other molecules which are around it. Because remember, what we're looking at here, we're not concentrating on the chemical bonding between the atoms which make up the substance. What we're going to be looking at, or have started to look at, is the interactions which happen between the molecules which make up the substance. Because you live on an island, and I water my plants where I grow, water molecules don't exist by themselves, do they? You've got the sea, you've got lakes, you've got water that comes out of the tap. There must be something holding it together, and something that's holding it together is the hydrogen bonds. Okay, so moving on to the next slide. So this word dipole and dipole moment. You see a lot of stuff in science. Sometimes students see these words, and people see these words, and it's a strange language. And people think, oh my God, it must be really difficult. And sometimes some of it is. Some of the maths and some of the numbers that there is in science definitely is. I know that because numbers are not my strong point. But the ideas and the concepts and what's actually being tried to explain to you, sometimes you've got to study it and look at it, but it's not actually that difficult once you actually turn down and look at the ideas. So what we're looking at here, this is one of those really important ideas, is a dipole and a dipole moment. A dipole really means a pair of separate but opposite charges, so positive and negative again. The dipole moment is the product of the positive charge and the distance between the charges, or it can be the product of the negative charge and the distance between that charge. A polar molecule, like water and ammonia, is any molecule which demonstrates or which has a dipole moment. Okay, this idea that you've got different charges on different charges inside the molecule. There's a separation of the substances, the atoms which make up the molecule, based on the chemical separation of charge, based on the chemical bonds and the charges on the atoms which make up the molecule. So what it means is that one bit of the molecule is going to be positive and the other part will be negative. If a molecule has that, if it has a positive end and a negative end, it's polar and has a dipole and has a dipole moment. And that's it. That's what that means. That's all it is. So we'll have some pictures to show this in a minute. So what does all of this have to do with hydrogen bonding? Okay, so to quickly mention this, some of the substances that we're going to be talking about today. We've talked about nitrogen and we've talked about oxygen. Another substance which is able to form, which you don't study at GCSE and you don't study really until you get to A level and go to university. Another substance which is important in hydrogen bonding is fluorine. So hydrogen bonding happens between fluorine, nitrogen, and oxygen. Now, if you're doing GCSE chemistry, you'll see that these 3 elements are in period 2. Nitrogen, oxygen, and fluorine are in there. That means they're in the same period of the periodic table. which means they have the same number of electron shells, but it also means they have different, but they have different numbers of valence electrons because they're in different groups. Who's doing GCSE in here? Or year 9 or okay, because I'll take that as a no then. Okay, that's all right. So
I think BJT.
okay. So there are so there are some of you there then. Good. All right. So I put this here. This is a fantastic resource. It's really, really good. It comes from a place called the University of Nottingham. And what happens is the fella's got the biggest hair I've ever seen in my life. In what he doesn't know about chemistry isn't worth knowing about. So when you click on the link, you'll see a periodic table come up. And what happens is you can click on any one of the chemical elements, and then what they do is they tell you about how the chemical elements work. So what you can look at with this is nitrogen, oxygen, fluorine, and any of the other elements that there are as well. So the elements we're talking about are in the same period, which means they have the same number of electron shells, but because they're in different groups, they have different numbers of valence electrons. Now, this idea of them being in the same, what it means is they're in the same place or the same area inside the periodic table. So it means that they have, you know, they have some connection between them. There are relationships between them. And the main of the relationship we're going to be looking at with these three elements is that they're very, very good at forming hydrogen bonds. And the reason they're very, very good at forming hydrogen bonds is because they've got a good, solid, strong dipole moment, which just means they're able to form compounds which have a different, which are separated, which have a positive end and a negative end. That's all it means. So ammonia, symbol NH3, a colorless gas made of three atoms of hydrogen and 1 of nitrogen. Three covalent bonds are formed with 3 hydrogen atoms. An ammonia molecule has the shape of a trigonal pyramid, and all that means is a squashed down triangle. Now, because it has this shape, the molecule is polar, which means it's soluble in water. It also has a very strong and pungent odor. If you've ever done any experiments in your classes at school, you'll know that. And it used to be used in smelling salts. And if anyone wants to know what smelling salts are, there's a link at the end as well, which has got that in there. Okay. Cool. Good. Okay. Right. I'm just getting used to using Zoom. That's why I keep looking at I keep looking at the chat room, so seeing what's there. I'm more nervous about using the technology than I am about talking to you or talking with you about the subject. So, which is why Miss Lewis is here, so to make sure that I don't fall over. Okay. Anyway, right, back to it. So, the next slide then. Here's a picture of ammonia. We've seen a similar picture here. It's much less dense with water. It has a melting point and a boiling point of those temperatures there. In liquid form, its chemistry can be compared to water, but of course, if you look at it, its melting point is -77, its boiling point is -33. So that means that, you know, at the temperature we're at now, it would be a gas at room temperature. But in liquid form, it does have hydrogen bonds because it has a negative end, which is where the nitrogen is, and it has a positive end, which is where the hydrogen is. So it is a polar molecule with a dipole moment. As with water, the hydrogen and nitrogen atoms each share electrons because that's what a covalent bond is. This forms the covalent bond. Ammonia as a molecule is held together by 3 single covalent bonds. Now, if you see these 2 electrons here, it has only 1 lone pair of electrons. Water has 2 lone pairs. And this is really important for what happens when nitrogen and water form hydrogen bonds. So water has 2 lone pairs and ammonia has 1. Okay, I just thought I'd mention this because it is important, because this idea, you're not going to get asked this in any of your exams at the level that you're at. They're not going to ask you about what any of that means. They're not going to ask you what the bond angles mean or anything like that. So don't worry about remembering any of this. It's just important to be aware that molecules, these kind of molecules that we're talking about, have a specific shape. And these are just some of the shapes that there are. And the reason they have the shapes is because of the way that the charge and is organized on in the substance, and the way that the atoms which make up the molecule bond with each other, and how it all works. So the shape of the molecule is predicted by this set of theories called VSEPR. There's a link for it in the end, and don't worry about remembering that. You won't need to. What it means is that the valence electrons, that's the ones that are responsible for bonding, so the ones in the outer part of the molecule, orientate around the central atom, whether it's carbon, whether it's nitrogen, oxygen, fluorine, whatever it is. And what you also get though is that the repulsive effect of the negative charge on the electrons is minimized because the atoms are as far apart from each other as they can be. Or you can turn it around on itself and say that they're as close together as possible. It depends how you want to explain it or how you are being asked to explain it. So what you have is repulsion by negative charge, which is minimized, and the valence or bonding electrons are as far apart from each other as possible, as they can be. So compared to water, ammonia has at room temperature and pressure has a much lower melting point, much lower boiling point, density and viscosity. And viscosity just means how much it flows. The more viscous something is, the less it flows, the more gloopy it is. A bit like the difference between yogurt and water, say, that sort of thing. And ammonia is also less dense than air. Yogurt, sorry, would be more viscous than what water is. So ammonia is much less viscous than water is in the liquid state. It is also less dense than air, ammonia, and the nitrogen atom, as we've said, only has one lone pair, not two. And what it does, because it's soluble in water, when it dissolves in water, it produces hydroxide ions, which are just these ones here, and that makes it alkali. So it's a base when it dissolves in water. And if you're not doing GCSE or you're not even in year 9, don't worry about remembering this equation because you don't need to at the moment. But all it means is that ammonia dissolves in water and produces this substance here, which is called an ammonium ion and hydroxide ions. And it means that the reaction can go in both directions. But you do that much more at GCSE. And if you are doing GCSE, it's you should be familiar with that. Okay, so hydrogen bonding in water. Right then, hydrogen bonds are formed when a hydrogen atom is bonded to when a hydrogen is bonded to electronegative atoms. Those are ones that have got a negative charge. So it's a type of bonding which happens between molecules, not inside molecules, but between them. What happens is you have the attraction between the hydrogen nucleus, which is just a proton, so it's positive, and the lone pair of electrons, which are negative, on the oxygen atom or the nitrogen atom, if it's water or ammonia, in a neighboring molecule. So the molecules which are next to it, not inside it, but the ones which are not the atoms inside which make it up, but the molecules which are next to it. So here's a representation of hydrogen bonding in water. Couple of pictures. As we've said, each oxygen atom has 2 lone pairs of electrons. It makes hydrogen bonds with 2 different hydrogen atoms in different molecules. The oxygen atoms and the hydrogen atoms of different molecules are attracted to each other. The bond is possible because of the different charges on the atoms. So what all that means is you've got the positive hydrogen here and the negative oxygen here, and the negative charge on the oxygen and the positive charge on the hydrogen pull the different molecules toward each other. Now this hydrogen is attracted to a lone pair, which is here, and this hydrogen is attracted to a lone pair, which is there. And if it was carrying on, you'd have an oxygen atom there, and another oxygen atom there, and it begins to form a structure, if you like. So what happens is the positive end of the hydrogen here, as I said, attracts to the oxygen. This forms the hydrogen bond. This is what hydrogen bond is. It's an attractive force between the negative part of this oxygen of this water molecule and the positive part of this water molecule. And what this will form, so it's an intermolecular force, which is about the 10th the strength of a normal covalent bond. And covalent bonds are really, really strong, as are ionic bonds. But you do that much more when you study in much more detail what ionic and covalent bonds are. Okay. So in ammonia has only one lone pair of electrons and that's on the nitrogen atom. So what that means is because it's got less negative charge, ammonia is less electronegative than water when it's liquid. This means there are less hydrogen bonds. The bonds themselves are weaker because the difference in charge is much less. So what this means is it's not able to form a liquid at room temperature and pressure, which is why ammonia is a gas at room temperature and pressure. So in water, there are two lone pairs, more bonds, and they are stronger. Water is more electronegative than ammonia, and so water is a liquid at room temperature. So that's a real big difference there, and that's why at room temperature, water is a liquid, and it's still a liquid until you get down to 0 degrees. Okay, so comparing the two, water and ammonia. In water, the hydrogen bonding is much stronger in water. In liquid water, the bonds are constantly breaking and reforming. So at room temperature and pressure, water is a liquid, ammonia is a gas. And another reason for this is each water molecule can form up to 4 bonds with four other water molecules. In ammonia, it can only make 1, which is why water has a higher boiling point, melting point, density, and density at room temperature and pressure than ammonia does. In vapor form, there are no hydrogen bonds. Now I'll start that again. In vapor form, which means gas, there are no hydrogen bonds or any bonds at all between the molecules. Anybody suggest why that is? Why when it's a gas, there are no bonds between the molecules? Think about the particle model, kinetic theory, that sort of thing. Any ideas?
No, sir.
Go on, Em. All right, I'll tell you. It's because the particles are completely separate from each other. If you look at when you do what's called the particle model, solids, liquid, and gas. In a gas, the particles are completely separate from each other, so there's no bonds between them. Okay, I'm glad I put that in as a question at the end as well. So that's why I put it there, and I put it down at the end. Okay, right. Okay, moving to the next slide. Okay, this is another quick picture to show it in what we're talking about. Here we are, the water molecule. 4 bonds can form, 4 hydrogen bonds can form because it's got to, because of the way that the molecules organize themselves. And this is what they call sometimes liquid water and ice is sometimes called the perfect hydrogen bond system because the maximum number of hydrogen bonds is formed in each state. And by state, we mean gas, liquid, or solid. Whereas in ammonia, there's only 1 lone pair. So only 1 on the nitrogen atom. So in a group of ammonia molecules, there just aren't enough lone pairs on the nitrogen atom to bond with all the available hydrogen atoms that there are. So it can bond with 1 other, but there's still 3. But there's still 2. But there's still 3 hydrogen atoms available which don't bond with anything. So at room temperature and pressure, there are not enough hydrogen bonds to keep ammonia as a liquid. But whereas with water there are enough. And the only way that the only way that ammonia can be in liquid form is if the temperature drops to less than minus 77 degrees, and that's far too cold. So it stays as a gas. Yeah, and there's another quick slide to sum up this section. What we're saying is the difference in the number of lone pairs on each molecule determines the different physical and chemical properties of each molecule. Oxygen is in group 6, nitrogen is in group 5 of the periodic table. This also influences how the atoms of each element bond with other atoms and the physical and chemical properties of the compounds that they form. because they've got different bonding, which means they have different structure, which means they have different chemical and physical properties, irrespective of whether the nitrogen and oxygen atoms make water or ammonia. It has with all the compounds that they form. Okay, so hey, I meant to say this is an A-level picture. All right, it's the sort of thing, if you're doing GCSE and you're thinking about doing A-level, this is the kind of thing that that you look at. If you're not doing GCSE and you're not at A-level yet, don't worry about any of this at all. All these words here, don't worry about any of it. All you need to look at is this bit, the bit where it says the lone pair. There's one lone pair on the ammonia, two lone pairs on the oxygen, and a lone pair is two electrons which are not involved in chemical bonding within a molecule. What they do is they create the repulsive force, which is a strong negative one, because they're electrons. The electrons are just negative charge, and they're negatively charged. This makes them highly attracted to the positive charge on the hydrogen atoms on other molecules. So for what we're saying, what's trying to say here is, so for hydrogen bonding to happen, there has to be at least one lone pair on the molecule. If the molecule hasn't got a lone pair, it can't do hydrogen bonding. That's the kind of question that might come up in at GCSE. So a hydrogen bond definition, another couple of pictures for you to look at. A hydrogen bond is defined as a dipole attractive force that exists between polar molecules containing a hydrogen atom covalently bonded to an atom of nitrogen, oxygen, and fluorine. And that's the point of all of this. It only really happens with nitrogen, oxygen, and fluorine. It doesn't really happen with other substances. So as you can imagine, there's a whole branch of chemistry which only concentrates on hydrogen bonding. Okay, so a quick thing. We've mentioned the shapes a few times. Covalent molecules and ammonia and water are covalent molecules, but all covalent molecules have a specific shape. What happens is when they form the covalent bonds, the sharing of electrons produces a fix in the area where the bonding is happening, where the valence and bonding electrons are happening. It is the repulsion and the orientation around the nucleus of all of this which gives the molecule its shape, all the shapes that you saw in the previous slide. Ammonia and water have the same number of electron pairs around the central atom, but they have different numbers of lone pairs. Okay, so in the shape of ammonia and water, what we have is this. Now, a water molecule has the two lone pairs on the oxygen atom, and the ammonia molecule has the one lone pair on the nitrogen molecule, on the nitrogen atom. Sorry, that should say atom. That should say atom. That should. The repulsive effect of the negative charge on each set causes the water molecule to have a V shape, and the ammonia molecule to have the squash shape that it does. And I just wanted to say, just to point out, this means what happens here with this is that substances exist in a 3D space. What these lines mean is that when you see this wedge shape, what it means is, or if you ever see this wedge shape when you're looking at any of this on YouTube or on your documentaries that you see, anything at all like that, all atoms, all molecules, all compounds, all substances exist in a 3D space. So what that means is, if you see this wedge shape, if this was a 3D computer, you'd be able to see the hydrogen atom be coming out at you. The one behind you, the wedge shape going that way, means it would be going backwards. Okay, so they exist in the 3D shape. Okay, so that's just a little important point that's for you to be aware of. And you can see what the shape of the molecules are: water, ammonia, and methane, which is a gas, which is the simplest alkane, a gas. Okay, so again, the shape, there's not just another picture to show it again. Again, you're not going to get asked about any of this, what the bond angles are, what the bond lengths are, or anything like that. Not at this stage. The shape of covalent molecules caused by these interactions is hugely important in biology and the chemistry of life, because it influences which interactions are going to happen under a specific set of conditions and which ones don't. And that's why all of this is so important. And hopefully this is the bit where the theory you've just seen gets applied to the real world. So this is the bit where, you know, the theory, as I said, gets applied. Okay, a molecule of water has the angular shape, the V shape we talked about, which causes the permanent dipole moment. Another word here, just because it's so strongly hydrogen bonded, it has what's called a high dielectric constant, and that's just a fancy way of measuring how polar the molecule is. All it means is that the higher the constant, the more polar the molecule is. And water, because it's the most polar molecule, has a higher dielectric constant than ammonia. These properties make water a very powerful solvent for polar and ionic compounds. Well, that's just a fancy way of saying why so many things, so many substances dissolve in water. You'll see water referred to as the universal solvent. That just means it dissolves a lot of stuff, a lot of different substances. Okay, so at room temperature and pressure, the melting point of water is 0 degrees. With ammonia is -77. So at room temperature and pressure, water is a liquid, ammonia is a gas. In the natural world, ammonia is produced as part of the nitrogen cycle even. It's an essential part of that process, and you do that at GCSE, and you certainly do it if you go on and do A-level biology or chemistry. It is released to the atmosphere in the nitrogen cycle, or it dissolves in water, where it forms various compounds which are essential and useful for life processes. In nature, ammonia doesn't exist in high concentrations because it's so toxic. It will poison things. So why is all that important? There's a quick picture of the nitrogen cycle, and here it is. There's a link for it as well. It's one of the biogeochemical cycles, and is an essential driver for life on Earth. And if you were at the climate lesson, climate session last month, what a biogeochemical cycle is would have been explained. So what happens in the nitrogen cycle? Ammonia is produced in the nodules, in a special part of plants called leguminous plants. It's made in a process called the Haber process. But when we make it, when human beings make it, we need a high temperature and a high pressure. When the natural world makes it, when plants make it, it happens at room temperature and pressure. So what happens is substances called ammonium ions are released into the soil, and these are then converted to nitrifying bacteria and to what's called nitrate and nitrite ions in the nodules of the plants. All that means is that ammonia is made in the natural world by plants, and it's important for that, and it's important to make some other compounds which plants need. Okay, so it's another particle representation of water and ammonia of ammonia and water. When it's the same process, same sort of idea. You can see that the positive hydrogen, negative and the negative charge on the nitrogen, produce of the polar solvent. Water is called the universal solvent, as I said, because it dissolves so many substances. If it didn't happen, if it wasn't polar, if things didn't dissolve in water, we wouldn't be here. Life on Earth just simply wouldn't be here. So when polar substances dissolve in polar water, sorry, I'll start that again. When polar substances dissolve in polar solvents, mainly water, the bonds between the solute particles, that's the thing that's being dissolved, are broken down because the positive part of one molecule here attracts the negative part of another. And what happens is, effectively, you get when the positive charge on the hydrogen ions attracts the positive charge on the hydrogen ions attracts the negative ions on the ionic compound. So this idea again of opposites attracting, in this case, negative attracting positive in water when it dissolves. And what happens as well, the oxygen has a negative charge, so that attracts the positive ions, or the positive part of the substance which is dissolving. So what happens is the solute particles, the substance which is being dissolved, are separated from each other because they have different charges. Water molecules are able to separate the particles in ionic solids from each other because the oxygen atoms form a shell, a cloud around the positive charged particles in the ionic solid, and the hydrogen atoms are attracted to the negatively charged particles in the ionic solid as well. So what that is this is an example of another fancy word of, it's just called solvation. Oops, sorry, called solvation. And what hydration is, which is any kind of solvation to do with water, is called hydration. Specifically with water. So another little interesting point, and this may well come up if you're doing GCSE chemistry at the moment, is dissolving is an endothermic process. And that is another fancy word, which just means when the dissolving happens, it takes energy in from the environment around it. So for example, when ammonium nitrate dissolves in water, which is just a soluble salt of ammonia, when that dissolves in water, the temperature of the water will actually fall. And this has been measured by experiment. And what happened, the reason that the temperature falls is because when it dissolves, the energy in the form of heat has been taken in from the surroundings. When the opposite of endothermic is exothermic, giving energy to the environment around them. So dissolving is an endothermic process because energy has been taken in from the surroundings. Okay, so and here's a quick representation of this idea of positive and negative attracting each other. So sodium chloride is a substance called common salt. It dissolves in water, and what happens is the positive part of water, the hydrogen, clouds around the chlorine because the chlorine has a negative charge, whereas the oxygen part of the water clouds around the sodium because the sodium has a positive charge and the oxygen has a negative charge. So polar substances are any substance which has a different charge at opposite ends of the molecule, and ionic solids are good examples of those. And ionic solids is any solid substance which is made of non-metals and metals bonding with each other. So and metals are positive, non-metals tend to be negative. Well, non-metals are negative, sorry, on charge. So yeah, and so that's what happens. Sodium chloride dissolves in water. The positive and negative parts of the particles attract each other, and the same happens with any ionic solid. All you have to do is remember which part of the substance is negative, which part of the substance is positive, and you can go from there. So you might get, if you're doing GCSE, you might get asked a substance that you've never heard of before, an ionic substance you've never heard of before. You might say to you, what happens to it when it gets dissolved in water? All you've got to do is remember what the charge is, and then from there apply your knowledge of how to balance the equations and what happens when the substance dissolves in water. And then it happens because the whole way it's allowed to happen is because it takes a little bit of energy. It takes energy to break the bonds that make up the ionic solid. But once the dissolving happens, energetically, the dissolved substance becomes more stable than what it was when it was solid. So there's an energy movement within when the substances break down. So there's an energy input to break down the solid, but the energy of the water, of the solution, balances with it. And there's a whole area of science called fluid chemistry, which we're not going into now. Okay, so we're getting towards the end. There's another quick representation here of what's happening. Non-polar substances are those that do not have a dipole. And they haven't got a dipole or a distribution of charge because they have no dipole because they have no uneven distribution of charge. And this is the key point. It's about the charge. One end of the molecule is positive, another end of the molecule is negative. The more the difference between the positive and negative is, the more polar the substance is. So non-polar substances don't form ions when they dissolve in water. Non-polar substances are examples of those would be organic compounds and giant covalent structures like diamond, or silicon dioxide, which is sand on the beach that doesn't dissolve in water, and the diatomic elements that there are, and the acidic gases like carbon dioxide, sulfur dioxide, will dissolve in water and form ions, but nothing like to the extent that ionic solids do. And what happens when these gases dissolve in water is important environmentally too, but we're not going into that. Not going into that now. Okay, so this is important. This is a handy if you are heading into a GCSE exam soon. This is a handy slide for you to remember. Remember that all salts of potassium and ammonium dissolve in water. All nitrates, all chlorides except the ones mentioned, all sulfates except the ones mentioned. Some of these smaller covalent substances will. And remember, when nitrogen dioxide, carbon dioxide, and sulfur dioxide dissolve in water, they form weak acids, so they're called acidic gases. Larger covalent compounds, which are some of the ones that we mentioned, like diamond, silicon dioxide, sand, won't dissolve in water because they are non-polar, and because the intermolecular forces between them are so strong. And the reason for that is because there's so many particles which are so many molecules which make up the structure. Okay, so think about diamond, think about how big it is. It's called giant for a reason because they're huge and make these big, huge crystal solids. So that's why they don't dissolve in water. If the water can't overcome the intermolecular forces like it can with ionic solids, and it can't do it because it can't do that because there's not enough uneven distribution of charge. Okay, so in liquid water, hydrogen bonding pulls the water molecules closer to each other than they would be if they didn't exist. This produces a high degree of structure and order, and the most ordered and densest form of liquid water is about 4 degrees. In the solid state, ice, the order and density decreases. So, and this is really unusual. I've been talking and communicating about science for the last 20-25 years. At room temperature, at 0 degrees freezing point, I don't think that there is, on the Earth anyway, I don't think there is any substance I can think of where the solid form of that substance is less dense than its liquid form. And this is crucial for life on Earth. You might not think it, you're thinking, it's just water, but it has all these properties which make life possible. And that's why hydrogen bonding is so important, because liquid water, one of the reasons it's important, liquid water is more dense than solid water, or solid water is less dense than liquid water. Depends how you want to look at it. Okay, so there you are. If it wasn't so, why do we have icebergs? And why is it that the fella can sit on the ice there like he is on the right, and why doesn't all the ice fill into the lake? So ice, or solid water, is less dense than liquid water, which is why icebergs don't sink, but float on the oceans and gradually melt. It's also why ice on a lake or pond doesn't sink and can support the mass of other objects, support the mass of other objects too. Like the fellow is sitting down on his chair there and ice skating. And if you do ice hockey on a lake, which I wouldn't recommend, but there you go. But the question of all of this is why? And that goes back to what's going on inside the molecules. So what happens is, ordinary ice has an open structure built of 6-membered rings. You don't have to remember this right now. Each water molecule is tetrahedrally bonded to 4 others. So you can see that when you look at some more pictures coming, you can see that in ice, each water molecule is bonded tetrahedrally to four others, and that just means it makes a tetrahedral shape. So what happens is, as the temperature gets towards freezing, 0 degrees, the arrangement of hydrogen bonds changes, and more of them begin to form. This forces the water molecule apart because of more repulsive forces. So it's those lone pairs again, which are pushing the water molecules around them further away. So what happens is, as we get to freezing point, ice expands. Whereas with most other substances, the opposite happens. It contracts. So what happens is, as ice expands, you have the same number of particles or same number of molecules occupying a bigger space, which makes them less dense. So back to the question, why does ice float? ice is less dense than water. So also in ice, the hydrogen bonds don't form and reform like they do in water, because they have less heat energy than liquid water water molecules do. At below 0 degrees, water is no longer a fluid, it's a solid, so the hydrogen bonds become permanent and expand, pushing the entire structure outwards. This makes solid water less dense than water. Like I said, that's why I put this in red. See if you can find any pure substance, and this is key, pure substance, which is a liquid at room temperature, which behaves in this way. So what substance can you think of? I can't think of one where the solid form, where it's pure, where the solid form is less dense than a liquid form. Because I can't think of one. I've never been able to find one. Of course, what you'll do now is come back to me in about a week from now and say, oh, look, I found something, which wouldn't surprise me at all. Anyway, this is important as well, because the water underneath the ice is more toward freezing than water which is not. What happens is, like in the lake that with the picture above, you get an insulating but transparent layer which keeps the water temperature constant. The layer traps air, so but also allows sunlight to pass, so photosynthesis can carry on, which means the oxygen can still be produced in the water, which means life can carry on even in winter. When springtime happens, the ice melts very, very slowly, and water is gradually reformed and released back into the system, into the lake or pond or whatever it is. It takes because if you're doing physics, you realize water has what's called a very high heat capacity, and all that means is a fancy way of saying is it takes a lot of heat to melt the ice, and this prevents sudden increase in temperature. Now, if ice was more dense than water, think what would happen. What happens when you put a stone if you drop a stone on a pond, or you drop something heavy that doesn't float in water? It sinks to the bottom, doesn't it? Imagine if ice and water didn't interact in this way. Imagine if what happened was, when it got cold, that all the water froze. What would happen then? The whole water column would freeze, and you'd have nothing in the life wouldn't be able to carry on, because it would get warm in the summer, cold in the winter, and everything would be destroyed when the ice got cold. When the water froze. So it's essential for life on Earth. This whole process is essential for life on Earth. It didn't happen, we wouldn't be here. So it also means that the physical and chemical properties of water at room temperature and pressure cause this phenomenon called surface tension, which is just a fancy way of saying the tendency of what molecules to shrink to the lowest area under a given set of conditions. There's a link which explains all that. If you're doing biology or thinking about doing biology, hydrogen bonding happens in DNA. If hydrogen bonding didn't happen, DNA wouldn't exist. It also occurs in proteins, which are various chemical, and in biological molecules in general. So it's crucially important for biochemistry and therefore life and evolution. So it's important stuff. Okay, wrapping up now. Polar substances are said to be hydrophilic. Hydrophilic just means that they like water. I have to put the question in there. There's a link there to help you answer it. Non-polar substances are said to be hydrophobic, which means they don't like water. Why is that? Polarity, this idea of difference in charge in substances, is crucially important to the formation of cell membranes, and the organelles, the tiny little organs which are inside cell membranes. So that's the nucleus, the mitochondria, the Golgi apparatus, all those sorts of substances. So what we're saying is, what's being said is whether a substance is polar or not, is polar or not, influences its role in the biochemistry of organisms. And that just means what's going on inside you, the chemical reactions, biological and chemical reactions which are going on inside you, and the processes which are going on, and in other organisms too. And across the environment and the natural world in general. So, and finally, the last one, I would not be doing my job properly if I didn't mention this. Water vapor as a gas, that means water as a gas, is highly absorbent of infrared light, but very transparent to ultraviolet light. This makes atmospheric water vapor, basically clouds, a key component of the natural greenhouse effect. It also means, so in daylight hours, light from the sun in the form of ultraviolet radiation can pass through the atmosphere, but when it's reflected from the surface of the Earth, it's trapped in the atmosphere, and the heat is then pumped out in all different directions. Apologies for that. This is why when clouds are not present, is why even on very, very hot days, it can get really, really cold at night, even in the desert. And that is really it. So what I've done right at the end is put some questions at the end. Now, with these, don't feel that you have to sort of answer them or treat them as homework or anything like that. You can if you want, you know, but you don't have to. These are there just to make you think about a little bit about what's we've been about what's been said tonight. And that's it. Okay, so everyone you will get a copy of all of this. You get the recording, and on the very last slide there's some links as well that are in here as well. Now, just to say to you, I really like bite size because it breaks everything down, but I'm becoming very, very fond of this site here, ThoughtCo. Have a little look. It's written by people who've got what's called PhDs and doctorates and qualifications in science in their various areas. And the people who put these sorts of articles together know more about science than I ever will. But and they explain things really, really well. So yeah, there we are. I hope that you got something out of that. So yeah, I'll leave it there.
Excuse me?
All right.
You were saying about the density, how most liquids become less dense as it freezes.
Yeah.
I saw a video like a week ago about someone says that they were drinking heavy water, and the chemical formula for it is D2O, and it's one of the only liquids that becomes less dense as it freezes.
Yeah, that's right. It's what heavy water is. So remember on the slide right at the beginning, we mentioned, we sort of showed you that slide with the three types of hydrogen that there are. Heavy water is called tritium, and I always get this wrong. I'll say it wrong. It's called tritium and deuterium. And what they've got is different isotopes inside. Different numbers of neutrons in the nucleus. So they're isotopes. And what that means is you're right, because it's still water, but it's got neutrons in the nucleus, and that's what makes it heavy. So it's got a particle. They've got particles inside their nucleus that are called neutrons, which normal ordinary hydrogen doesn't have. The hydrogen we know doesn't have, but it's still hydrogen. It's just got neutrons inside it.
Yes, sir.
So it does, and it still expands when it freezes. Okay. Okay then. So yeah, I certainly enjoyed putting that together. I certainly enjoyed talking with you. Some of you asked about the notes. You do get the notes. You do get the recording. If you have any questions about what's said on this or anything about the links that are on there, please do ask. That's what we're here for.
Yes, sir.
Appreciate it, sir.
Okay. Everybody happy? Any questions? Anything else to add?
Very understandable.
Thank you. Yeah, it's I got the part of the reason that I wrote it or put this together. It's because when I was at university, many years ago, one of the questions that they asked was explain theoretically how it would be possible to have life based on ammonia, and that's one of the questions that's on the back. What kind of conditions would have to exist theoretically for life to be based on ammonia, in terms of hydrogen bonding, in terms of all of the things that we've talked about in the presentation. Okay. So what we're hoping to do is make this a regular thing. I'll have a word with Miss Lewis and see what she thinks. And if any of you have got anything, that you want to do, please do come and let us know. And we'll either put lessons together on it, or workshops on it, or presentations like this. And because it's your learning as much as it is me putting all of this together.
Yes, sir.
Okay,
Thank you very much.
no worries, anytime.
Thank you.
Thank you.